Hello everyone, my name is Neha Kardam and this is lecture 23 on Introduction to Automation. In this lecture, we'll continue our discussion of AC motors. So today we are going to start with a synchronous motor, and this is one of the AC motors. And this synchronous motor, as you can see on the screen, may seem similar to more common induction motor. However, there is a crucial difference. In synchronous motor, the rotor rotates at a precisely the same speed as the rotating magnetic field, and there is no slip in synchronous motor. What does it mean? It means that the rotation of the motor shaft is synchronized with the frequency of the supply current. Or in other words, we can say that if the supply frequency is 60 Hz, the synchronous motor will rotate at exactly 3600 revolution per minute. And this synchronization feature makes synchronous motor extremely desirable in industrial settings where precise speed control is very important. For example, let's say in the conveyor belt system, where multiple motors must operate at exactly the same speed to maintain the smooth operation. But synchronous motors, they are not just limited to industrial applications. They are also extensively used in smaller, low power application where precision and the synchronizations are critical. For instance, in timing mechanism, they are also used in clock motors and positioning machining machines, where high precision and exact relationship between the frequency and the speed are very important. Now, moving on, our discussion of synchronous motors. In synchronous motor, it is important to understand how they are different or differ from the induction motor in terms of power transmission to the rotor. So as we have previously discussed in our last lecture, that the induction motors, they rely on induction for power transmission to the rotor, which necessitates difference in speed, which is our slip between the rotor and the rotating magnetic field. However, in case of synchronous motor, the power to create a magnetic field in the rotor, it must come from an external source. And this is achieved through the use of slip rings and brushes, which provide a means of delivering the DC power into the rotor. Now, in synchronous motor, this slip rings and brushes may sound a little familiar, but they resemble to the commutator assembly, which are used in the DC motors. Um, and and there is a key distinction in that in synchronous motor is that the electrical contact from the stator to the rotor is basically made through a smooth rings rather than the multiple contacts which are found in DC motors commutators. And this difference in construction ensures a continuous and a smooth electrical connection between the stator and the rotor, allowing for the transmission of DC power, which is necessary to create the magnetic field in the rotor. So we learned that in synchronous motor, it requires the slip rings and the brushes. Uh, uh, and its assembly is a little bit slightly different than the DC motor. Now moving on, so synchronous motor is not a self-starting. So let's delve into the various methods which are used to start the synchronous motor. As they require additional hardware for initialization. So some of the common techniques are, first is the variable frequency start. So this method involves gradually increasing the frequency of the power supply to the motor, starting from a slow speed and then speeding up. And this approach ensures that the rotating field does not outplace the rotor, allowing the rotor to be continuously pulled in just one direction. While this method offers precise speed control, it requires um, uh, extra electronic systems to provide the variable frequency. Next is our pony motor. And pony motor is another method in which uh, uh, often in which another motor is used, and it is often referred to as a pony motor. And initially it brings the synchronous motor up to speed by using this pony motor. So this pony motor, or we can say the secondary motor, is typically a small induction motor with two poles, and it allows to reach the synchronous speed of the synchronous motor. And once that synchronous motor reaches to the synchronous speed, the power supply is switched and the pony motor is disconnected. And next is our squirrel cage rotor bars. So some synchronous motors, they incorporate squirrel cage rotor bars similar to those used in the induction motor that we saw in the previous couple of the lectures, and they are used in the rotor. So these bars, they allow motor to start as if it were an induction motor, providing an easier starting process, and then it basically behave as a synchronous motor. And then we have finally the damper winding. So in some synchronous motors, it uses a damper windings consisting of a heavy copper bars which are inserted into the slots of the rotor poles. And these bars are short-circuited by the end rings, and it forms like a squirrel cage windings. So initially, when a three-phase supply is connected to the stator, the motor starts as an induction motor, and once the synchronous speed is reached, DC excitation is applied to the rotor, allowing the motor to continue running at a synchronous speed. So these are the four methods that we saw to start the synchronous motor. In addition to these methods, there is another thing which is used called the prime mover, such as an induction motor or DC motor can be used to drive the synchronous motor. So we can basically use the induction motor or a DC motor to help start the synchronous motor. And once the synchronous speed is reached, then the induction motor or the DC motor, they are disconnected. Now moving on is the power factor correction, and we are going to see its relationship with the synchronous motors. The power supplied by the power company, which arrives with the voltage and current in phase with each other, which is the most efficient way to transmit the power. And this alignment ensures that the maximum power transfer happens. And as the power is, we know that is the product of voltage and current. When voltage and current are exactly in phase, the power factor is 1. And this indicates that all the energy supplied by the source is consumed by the load when the power factor is 1. However, in real world scenarios, the power factor may deviate from 1 value, and let's see the first see the formula for the power factor, which is equals to the true power in kilowatt upon the apparent power, which is in kVA. So in real world, this power factor may deviate from value 1, and this is due to the factors such as reactive loads. So due to the reactive loads, when it is introduced, reactive loads, basically they introduce a phase shift between the voltage and the current, and which and thus leading the power factor less than 1. So the power factor value become less than 1 when there is a phase shift between the voltage and the current, and that is due to the reactive load. So a purely reactive load with a 90-degree phase shift, phase shift between the voltage and the current results in a power factor of 0. So when there is a phase shift of 90 degree, then that may result in power factor of 0, and indicating that no real power or the true power being consumed by the load. And in case of inductive loads, when they are inductive loads such as those which are used in the industrial application, they create a lagging power factor, while capacitive load, they create a leading power factor. So these two are very important points, that the inductive load, it creates a lagging power factor, and capacitive load, it creates the leading power factor. Now to address the power factor issue, synchronous motor can be used strategically. So by adjusting the rotor excitation current, a synchronous motor can be made to present a capacitive load, thereby improving the power factor of the plant. So this capacitive load that it will try to maintain the power factor to 1. Now, in synchronous motor, it installed synchronous motors installed specifically for power factor correction purpose, and when they are used for power factor correction purpose, they are called synchronous condensers. And these motors, they do not drive a load. Instead, they operate to spin and provide just capacitive reactive power to improve the overall power factor of the system. So we learned that synchronous motor can be used as a synchronous condensers, and which provide the function of a power factor correction, because if we have the power factor 1, then we can have the maximum power transferred from one point to another. Now let's explore the characteristics and the operation of the small synchronous motors. So the small synchronous motors, they find widespread use in various applications, ranging from the timing or clock motors to providing rotary power in instruments and small machines. These motors are available in different drive configurations or with attached gear trains, offering flexibility in their application. Now, in many small synchronous motors, they operate as split-phase motors designed to run on single-phase AC power with the assistance of or with the help of a capacitor. And this setup that you see over here, this setup enables them to rotate in either direction based on the switching arrangement. So you can see there is a switch. If the switch is on the upward side, then there will be a clockwise movement, and if this switch is at the bottom, there will be a anti-clockwise movement. So this switch arrangement as shown, so we saw that motor can rotate in either of the direction. So now just repeating it again, when the switch is at the up position, winding 1, the one winding that you see receives the line voltage, while the winding 2 is phase shifted through the capacitor, and this causes the motor to turn in one direction. And conversely, when the switch is in the down position, then this winding 2 receives the line voltage, and winding 1 is driven through the capacitor, resulting in rotation in the opposite direction. So the direction will be in the anti-clockwise. So this middle position that you see over here, this middle position of the switch turns the motor off. And unlike the large synchronous motor, small synchronous motor do not use electromagnets in their rotors, which eliminates the need for slip rings, and instead the rotor is magnetized through alternative means. And there are three common designs of three common designs that are used. The first one is called the reluctance motors, second one is the hysteresis motors, and the third one is the permanent magnet motor. Now of particular interest is among all three is the hysteresis motor, which features a smooth round piece of steel as the rotor, and operation is characterized by the smoothness and quietness, making it ideal for applications such as tape drives. So in conclusion, we can say that the small synchronous motors, they offer versatility and reliability in various applications with different designs catering to specific requirements. And some of the examples are given on this picture of the small synchronous motors, as you can see. So now this is the end of the lecture. Thank you so much for listening to me.